Okay, yeah, I prepared a few slides, but yeah, I'm trying to keep it short and yeah, hopefully have more time for just discussion and getting input from everyone. So kind of the goal of today's meeting is to show the kind of computations that we're doing in Monty, especially the ones that are taking a lot of time, and then seeing if the mega team has any ideas of how they could be sped up, if we can maybe leverage some of their work, if we can maybe leverage sparsity or any other techniques that you know of. And then maybe at the end of today, we can also think about if it would make sense to have some more mega Monty cross team meetings and if there are any synergies between the teams. Yeah, sounds good.
Yep.
Cool. All right. Yeah, as I wrote, no one needs to have any prior knowledge about what is actually happening inside of Monty. But I'll just give a quick outline of where we're at right now and what's going on in relation to runtimes and the kind of operations we're running. So at the moment, if we have a learning module that knows about 10 objects, it takes about 0.1 to 4 seconds to perform a step. A step is basically getting one observation from the environment and then using that observation to update the internal state of the learning module. And in order to recognize an object, you usually need to perform many steps.
Is it in serial or is that in parallel? Are you running on multiple CPUs?
I'll get to that in a second.
Okay. All right.
And will you also explain why there's such a big range from 0.1 to 4 seconds?
Yeah, so it depends on how many hypotheses are being initialized. So, for example, depending on how noisy the observation is and what part of the object the observation is on, it initializes different amount of hypotheses, and then different amounts of hypotheses need to be updated at every step.
Okay.
Yeah. Then, if we have 5 learning module, that number gets multiplied approximately by 5. Here I don't have a range because I just took the average from one experiment right now. But yeah, on average, they are about 2.5 seconds per step. If we know about 77 objects, it gets a lot slower because now we have to update evidence for every of the 77 objects. So about 1 to 15 seconds per step. And for 5 learning modules, it again scales by about a factor of 5. Now, given that we have to take multiple steps to recognize an object, when the learning module knows about 10 objects, you usually have to take less steps because there are less objects to disambiguate. So it takes about 0.3 to 3 minutes to recognize an object. If we have a set of 10 distinct objects, if we have 10 very similar objects, it can take up to 15 minutes to recognize an object, which is quite long. And then for 77 objects, really depending on which object we're looking at and how similar it is to other objects and how ambiguous the viewpoint is, it can take between 1 to 86 minutes to recognize an object, which, yeah, I think we can do a lot better. And I feel like we also need to do a lot better if Monty should ever be applied in the real world. We need to be able to recognize an object in less than 86 minutes.
Like the one from the soccer game, right?
Yeah.
Okay. Yeah. Okay. I'm sorry, just to say, are these times, I know you said you're going to talk about it later, but are these times single CPU or is this like this is Lambda using whatever CPUs you want?
Yeah, so in these times are from running on Lambda with 16 CPUs.
All right.
Okay, just quickly about the terms. So we have steps. That was the first numbers I showed. So one step is getting an observation, updating the internal state, and then moving. And then you get the next step. We have a variable number of steps in an episode. An episode ends, for example, if we recognize the object, or if we recognize that we don't know this object. And then we have a number of episodes within an epoch, which in our case is always going through the whole data set of objects once. And then we can run multiple epochs, for example, testing different orientations of each object. So steps in a typical experiment. First of all, we loop over episodes in an experiment. And this part, Ben actually nicely parallelized. So if we're evaluating, we can run every episode in parallel on a different CPU on the Lambda node. That doesn't work during training because when we are learning, it matters, the order matters basically. But since right now we're mostly evaluating, this helps speed up that part. And then while we haven't reached the terminal state yet, we first go over all the sensors that the agent has and collect the observations from these sensors. And then we loop over the learning modules and perform a matching step for each learning module. This loop could also be parallelized, but it isn't right now mostly because no one has done it yet. And we thought it's not the highest priority because we don't have as many CPUs as episodes anyways. So yeah, just wasn't the highest priority yet. And then for each matching step within one learning module, we have to loop over the objects in memory. And for each object, we have to update the evidence given the observation. The loop over objects, for this we use multi-threading, and then the evidence update is vectorized, so it's mostly large matrix multiplications. Then the learning module sends outputs. That's an output of the object it thinks we're on, its pose, and then a vote and a motor command. Then we loop again over learning modules. Learning modules receive votes, could again be parallelized, and then receiving votes again has to loop over objects and update the evidence using the vote. So here again, for the loop over objects, we use multi-threading, and then the evidence update is vectorized. And then finally, we check whether we reached the terminal condition. Getting the sensory observation takes about 0.01 seconds. It's pretty fast compared to the rest. This is the slowest step, updating the evidence for each learning module given an observation. So that takes about 0.01 to 0.05 seconds per object. If we scale that by having to do it for 77 objects and 5 learning modules, it adds up to about 2 to 5 seconds. With multi-threading, it takes about 1 second. And then the update using votes is a bit quicker because we don't use as many, we kind of threshold the votes to make it a lot faster. Overall, it takes about 0.05 seconds with multi-threading. If we do use all votes and don't threshold them, it is a bit slower than the first update. And then overall, taking as many steps as we need to recognize the object, it takes about 1 to 8 minutes for episodes where we don't time out.
So how many steps is that in general, usually?
It's usually between 20 and 200 steps. We have a maximum of 500 steps, which is when we reach timeout. Yeah, so since we already have these outer loops parallelized or use multi-threading, for this presentation, I'll focus on the evidence updates, which are the slowest part of the code at the moment. Is this clear so far?
Mm-hmm. Mm-hmm. Yeah, very clear.
I had one question. When you say multi-threading, what mechanism are you using for multi-threading?
We use Python multi-threading, the map.poolmap or something it's called. I'd have to check real quick. Yeah, we use this threading.thread.
Okay, so
That is not preemptive.
Okay,
Is
so
this you-
what?
Is this using Python threads then, Louis or Kevin?
Yeah, this is Python. This is Python thread. That's not preemptive threading. That will be.
Yeah, so these are not real threads.
No, there'll be a lock in the GIL.
Yeah.
Yeah, so that's why I was kind of asking, because at deeper levels, you want to distribute things. You can use affinities and various things, because basically at any one CPU, you only have direct hardware support for 2 threads at a time. Anything more than that is basically put into queues. So,
Yeah.
but if you're using Python threads, like Luis just pointed out, it's not the most efficient mechanism possible for the hardware.
It's only running on one CPU, I think. It's not even real threads.
Correct. It's yielding. It's yielding the.
Okay, so when they say they're running on multiple CPUs, how is that being distributed then?
Well, the episode is running multiple processors.
Yeah, so this is the parallelization part here. Each episode is its own process. And then within that process, we do the multi-threading.
Yeah, it seems to be doing something with multi-threading, right? Because it's up to 5 times faster than without it, right? So
yeah, it's definitely faster.
So it seems to be doing some goodness.
So it can't be one CPU then.
I mean, it depends. I mean, I think we need to wait until we see what's going on under the hood, right? Because
Well,
the different
also
types of
depends on if it's
multi-threading will be
blocking.
impacted by different things, right? So depending
Well,
on what the operators actually are.
The only advantage of that thread is there's some IO. You like, because it's going to do yield to GIL, and GIL is going to wait just for the IO. There's nothing else that it waits for.
Yeah. So let's look at the. I think you were going to talk about what's in the actual code, right? And then we can sort of back up a level if that makes sense.
Yeah. Okay, so if we actually run a profiler on one episode, so in this episode we have 5 loading modules, and this is looking at this is not using multi-threading just because the profiler doesn't deal well with that. So it's a bit slower than it usually would be. But anyways, it looks at the time taken by the top 15 functions. And as you can see, the longest time is taken by the KDTreeSearch, which is the first
Is that a
topic.
Python KD tree? Is it like, is
yeah,
that included in Python? Okay.
Yeah.
No, it's
it's using the C on it. Yeah, SciPy.
Okay. All right.
Yeah, so basically today I have basically two topics of things that I think could be sped up. One is, this KDTreeSearch. And then the second one are the
Everything else. Yeah.
Everything else, exactly. So yeah, like all the matrix multiplications, all the like evidence updates that are vectorized. And then there are a few other ones that are mostly like rendering the observations in Habitat and adding an object and things like that. And this one, I think I can figure out on my own. So yeah, let's jump in on the first one if there are no questions for now.
Yeah, I've used KD trees a lot. So, I mean, mostly in C++ implementations. So I can take a look at that. I don't know how SciPy implements it. Usually SciPy implements a lot of their stuff with C on the back end. And this just they provide a Python interface. So I'd have to look and see how that's being done.
So the SciPy one, I checked the one and we upgraded SciPy, so use the C backend. So we had to upgrade a version of SciPy so we could use the C backend.
I guess it's probably a pretty decent implementation.
Yeah, so I guess one question would be if there's actually if KDTreeSearch is actually the best way to get what we want, or if there's maybe a better.
What are you using it for? What are you using it for right now?
That's the next slide.
All right, cool, got it. Is Einstein like Einstein summation, or is that like an eigenvalue summation, or something else?
Yeah, Einstein is I'll also show that on a slide. It's
Okay.
yeah, basically doing a dot product with 3 dimensions.
Mhm.
So yeah, let me just go ahead. So yeah, first of all, the shapes and sizes of the matrices that we're working with, just as a primer for the next slides. So we have number of points in the model, which is usually around 500 to 5,000, depending on the size of the object. We have the number of hypotheses, which is between 2 and 8 times larger than the number of points in the model. We have the number of nearest neighbors that we look at. Usually it's either 5 or 10. We have the number of features that the sensor module is detecting. It's usually between 5 and 15. And then we have the number of incoming votes, which if we only take the highest percentile of votes, we have about 1 to 200. If we use all votes, it can go up to 200,000, which is then a lot slower.
Well, it's like a small metropolitan area.
I don't understand how the incoming votes can be that high. What's the logic? How they get that big?
It's basically all the possible hypotheses. So if we have 4,000 hypotheses from 5 learning modules, it's 40,000 times 5 incoming votes for possible poses.
I see.
And that's like in the worst possible scenario, the worst possible
Yeah.
case where everything is equally probable or likely to be happening.
And the hypotheses aren't the hypotheses are the hypothesis of the locations on objects. So it could be, you're saying, there's a limited number of objects. There's a lot of places.
Locations and pose, right?
Yeah, so that's why hypothesis is like 2 to 6 times larger than points in the model, because for every location on the model, we have 2 to 6 possible poses.
Right. Got it. Thank you.
Yeah. Okay, so finding the nearest neighbor. What we do right now is use KDTreeSearch. Basically, the problem we're trying to solve is we have an array of search locations. So in this picture down here, it would be given 2 hypotheses, the 2 gray arrows, we would have 2 search locations, the green dot up here and down here. So H would be number of hypotheses, in this case 2, and they are in 3D space, so we have XYZ coordinates. And then we have model locations, which would be all the black dots in here. That would be N, and then again in 3D space, so XYZ coordinates. And we want the IDs of the K nearest neighbors of these search locations. So for example, if K would be 3, we would want to have the ID of these 3 points in the search radius. So what we want to have returned is of shape HK.
Okay.
Yeah, maybe I'll pause here for a moment.
All right. So KD-tree typically works by doing a spatial bifurcation, right? You take half of the elements and put them in one side, half on the other, and there's like a dividing plane. Anything that's X less than this or X greater than that gets separated into a binary tree, and then you do the next one on Y and the next one on Z, and then you repeat.
Yeah.
And it's like an octree decomposition. Is that correct?
Yeah, so we basically built this location tree at the start of an experiment. So we already know the model of the object in this case, because we're just evaluating. So we built the KD tree once, and then at every step, we just query the tree with the hypothesis locations.
So you can stop that decomposition at any stage. Like you say, if I want to go until I have like only like 10 leaf nodes left, right? And then I can say, I can search through, that, or I can continue to decompose until I have only one object on each leaf node. That's one of the optimizations you can do in the KDTreeSearch is you can terminate it early if you want like a whole bag of things that are local, that are nearby.
Is that during building or querying?
Well, that's
That would be during building,
I guess.
That would be during the building phase. How many points?
That's like how it's structured.
Yeah, so the building is not that big of a deal because you only have to do it once. It's more the querying that's
querying,
No, but it would be a parameter you set during building that would affect the speed of the query.
Right.
Yeah, so we have leaf size set to 40.
Did you try to vary that to see if it speeds things up?
Yeah, Yeah, so if I set it lower, it was slower, but yeah.
How many points do you have in the again?
So N is around 500 to 5,000.
Can you just,
then-
I'm gonna ask the stupid question then, right? Can you just use a lookup table? We've got a bunch of memory on this thing, right? We've got 2 terabytes,
no.
right? Can I just
Yeah,
lookup
this
tables-
as a lookup table?
So the search locations are not identical to the locations in the model, so they're just like nearby. So before we used KDTreeSearch, we just did like the difference and then linear norm and then the minimum, and that was definitely a lot slower.
Yeah, you could do what Lawrence is saying, actually. Yeah, basically just create like this huge. You discretize the space.
Yeah,
You know, into the
create a
minimal
mesh.
and into a small mesh, and for each voxel,
You have your
just
neighbors.
have the list of K-nearest
yeah,
neighbors.
and at 5,000 elements, right? Even having 40, keeping the list of 40 is a small tree, right?
Yeah. And then
So
you just.
you don't store any mesh at all? Is that right? And there's no connectivity information between the adjacent points? Is this a
No.
list of points?
So I
Okay,
think
all right, yeah.
you can make it very fast.
Building a mesh would be one way of speeding that up a lot, because
Yeah.
for each point that you register, or even if you're detecting like a point like in between, like stored points, you can still figure that out pretty quickly by connectivity.
Yeah, so we do
Yeah, I
have a
think
graph.
I think Lawrence's idea is a good one, actually.
When would you create that list?
After training, at least it's
Instead of the tree, you just replace the
Yeah.
tree with this
yeah,
structure.
you replace the tree as a structure, right? And then it's basically a single
So, but
lookup,
it's
right?
done, you do your training and then you build a tree and
Yeah.
then all your inputs is based on. the
Yeah.
list.
Because it's static, right?
Simple, but really.
Simple, yeah. You've got a bunch of memory, right? Let's use it, right?
You just have to figure out
The
how to
other thing-
index in there.
Index, so the indexing is the tricky part, right? But as you say, if you know what your parameter space, your sort of spatial
Yeah.
space is, you just split it up, chop it up into bits.
Yeah, actually.
other
you
thing that
just
you can do to
discretize it, so they're
accelerate-
actually integers represent each voxel, you can just round and that's it.
Yeah,
That's your
yeah.
Index.
Yeah.
Round the things, yeah.
I think it'll be hella fast then, right?
The other
This
thing
on
you can do
search.
to accelerate it
Yeah, it's on
using this implementation you've got right now, a quick and easy thing you can do is to cache those nodes. So if you're only moving a short distance on the object for each step, you can reuse those lookups and go straight to the leaf node to see if your nearest neighbors are still in the vicinity. And
Yeah,
then
but
pop
Eric,
back
I
up
think,
if you
I think
lose it.
Lawrence's idea would take out all
Yeah, I
of
know,
them.
but
There'd be no tree to begin with.
Exactly, but I'm saying like if you just want to implement something just to accelerate what you've got right now, just to see if it makes any difference, is to cache the tree nodes that you're finding in the KDTreeSearch, and then just basically reusing those until they no longer are valid, and you pop back up, one node in the tree and go back down to find the neighbors.
I'm not sure that
I mean,
would
I'm
help
just
here.
saying.
That assumes you're gonna look at the same node over and over again in sequence. I'm not sure that'll help.
Well,
And
yeah,
I'm not sure
okay.
you even have access to that. with SciPy.
It's a locality, it's a locality based caching, basically, is what you're doing.
Yeah.
Yeah,
but you have to
if she's
take the
coding,
SciPy
then
implementation.
you're gonna see disparate stuff is the problem. It's not gonna be a
Well,
continuous.
yeah,
smooth
it
move.
depends on the length of this code, you're right, right.
Yeah,
Anyway,
but
so
also
that was just another thing I thought of.
yeah, but also it implies changing the KD tree implementation of SciPy. And I think that's
Yeah.
I don't think we want to get there.
So just so I get it right, what you suggested, Lawrence, you said to discretize the space into voxels and then basically just use those as a lookup table whenever we get a new point,
Yeah.
see
Yeah.
in which one it would fall.
That's what
Yeah.
Suicide said. I just said lookup table, right? I think he took it.
Well, that's what. See what
Right.
Yeah.
It's a voxel thing, but you
Um,
basically say, you know the point you're on, and you just look up all the adjacent points.
Yeah, but you'd have to, within the voxel would be, you just
Yeah.
say, within this resolution, I don't care.
Yeah.
I don't care what.
You lose that much resolution.
Oh.
You're not in
Yeah, right.
point space
Five
anymore.
points around me, I don't know which ones are close to which ones are close.
I mean, you could keep that.
Like you wouldn't,
Keep that information too.
whether it's 1.15 inches versus 1.16
Yeah,
inches,
yeah.
you might actually get different nearest neighbors, but
Yeah,
here you
yeah,
would still get
yeah.
the same. So it would be a slightly lossy, but that would be okay.
How would that
Yeah.
scale in some future? Do we want to worry about that now or does it matter?
I wouldn't worry about it.
Yeah, you can go. I mean, we've got terabytes of memory, right? Well, I mean, it's pretty small. It's like 5,000 bytes.
I'm thinking like scale, like, well.
At
If you
the
got 5,000 points, then
at the point it starts to fail, you can start hashing techniques.
yeah, you can hash as well.
Well, you know, the good thing about, I was trying to imagine, let's say we're scaling something human brain size, right? But the learning modules themselves don't continue to scale. They reach a maximum.
Yeah.
And so to make bigger brains, you need more learning modules. This just speeds up the operation of a single learning module, right? So that wouldn't, so my question, I've answered my own question. If you wanted to be really, really big brains, this wouldn't be the limiting factor.
Yeah.
No, and I wouldn't be surprised if neurons do something like this. That's essentially what they.
I was trying to think that. I was
Yeah.
trying to think, how does this relate to neurons?
Yeah.
I haven't gotten there yet, but you maybe reach a conclusion.
Yeah, I think it's very similar to what neurons do.
That makes me happy that my neurons are doing lookup tables.
That's basically what an SDR is. I mean, just within some resolution you match and then you do something.
Oh,
Right,
yeah.
right.
That's basically what we're talking about here. We're
So,
solving both your problems. We're solving two Monty problems. We're making it more neural as.
yeah, this is great.
Does anyone see an objection to this idea?
I mean, there might be a couple of other things algorithmically I could suggest, but if you're happy with the lookup tables, that's probably, yeah.
It does.
Good.
I think it's gonna be really hard to beat lookup tables.
Yeah, it's generally the rule.
Well, yeah, if you got the bandwidth for it.
The answer to the interview question.
Yeah.
The
Wow.
only
Still
thing I
have to
would,
search into that.
the only thing I would add to that is if you have 3 dimensions, there are several ways of creating the index. One way is just to, say, let's suppose it was all the indices were 256, and you have a 1 byte for the X, 1 byte for the Y, 1 byte for the Z, and so 3 bytes. The way you want to sometimes think about this is what the implication of that is on the underlying cache memory structure. There's an alternative format where you interleave the bytes. It's there's a name for it. I want to call it a Hamiltonian path. And what it does is it basically improves the locality. If you're hitting around one particular area, there's a greater probability that you'll be on the same cache line looking for the next one. And in fact, that's what they do in texture maps these days. So
Kevin, this is all in Python.
Yeah, like
I'm not
no,
sure
if you're going, no, you misunderstand. It's a simple bit twiddle on the index that you use to look something up.
but that
I think what we will have done with this is I think we'll have knocked down the runtime here such that now it's in the einsum and things like this, right? So you know what I mean? I think what would be cool is like try and implement this, see where the timing is, and then we can sort of do additional optimization. But my guess will be this will be like the 10 hottest operation now, right?
Yeah, I think the only concern I have is the resolution loss, because it's the right now we have pixel, we're going to voxel, right? So there's a volume in there.
Yeah, but if you're using sort of a uniform discretization of space, which is the other thing that you can do, is not the points are being separated by how many there are in each set, but like the space itself. Like if you know the max min dimensions, like a bounding box around the space, you can just subdivide it into like say 32 by 32 by 32 or 256 by 256 or whatever.
Right, but
and that gets you the voxels automatically, and it's the set volume to each one.
But like look at this picture, for example, of this mug. So that point that's marked in green will include the points that on the other side of the mug, inside the mug versus and the outside of the mug, because of the volume.
The voxel is encoded, the location of the voxel in memory is encoded in the actual XYZ coordinates or IJK coordinates of the point itself, right? You can actually read off where in that space it's going to be based on, basically the way I think of it is every time you divide the space in half, that's like a bit, either I'm on the left or the right side, it's either going to be a 0 or a 1. And so as I subdivide, basically you're adding another 0 or another 1, which you're saying, which side of the cut plane am I on? And effectively that drives you down to a single voxel, single leaf node, right? And so the position of the thing in XYZ space can actually read off exactly where it's going to be at in memory. So if you've got the memory space for it, it's a very, very, very fast lookup. It's a very fast hashing algorithm.
So in this case, would we basically not actually care anymore about storing less points because we just have like the discretized voxel space and we just want to say for every voxel whether the object exists there or not? Like,
Does the surface
how-
intersect the voxel? That's really what you want to store. A bit, the 1 or 0, does the surface of the shape intersect the voxel at this location?
Is that what we're
Yeah.
saying? I thought it was just replacing the KDTreeSearch.
Yeah.
Yeah, that's what I
yeah, we
thought.
still want to know. We still want to
Yeah.
know the ID of the point where we have stored the feature.
Yeah.
I think it's just to take the XYZ, hash it to an index
Yeah.
and look it up.
It's,
That's it.
yeah, I think what we're
It's-
proposing is like an optimization of basically given the tree is static,
Yeah,
let's just build a lookup table out of the tree, right?
exactly.
Could you make
Yeah.
it, if you wanted to do incremental learning, could you
You could still,
could
yeah.
you still modify
Yeah,
without
yeah.
rebuilding the table every time?
Oh, yeah.
Seems like you should.
Yeah, I mean, the stuff that people have done, something that, you know, Simtai and I were also saying LHS to each other, right?
Right.
So locality sensitive hashing is also a way that people do this, and you can do periodic rebuilds and all sorts of stuff,
But
right?
if
So
you have to rebuild all the table, can you just incrementally add?
incrementally build things, and you can also delay rebuilds and all sorts of things,
Yeah.
right? You can do minor
Could
twiddles.
you do actual true incremental learning with this table? Could you like, let's say, I'm going along, I find new objects, new points, whatever, can I dynamically modify the table without rebuilding it?
Yes.
Yeah, it'd be very simple.
Yeah.
So you're just modifying it very locally.
It seems like it gives you a lot of
Actually, back stuff,
flexibility.
yeah,
right?
to multiply the table.
You
as
know,
well, right?
Vivian was asking, can I have more points, but it seems like the size of your voxel could be modified too, and
Yeah,
It's actually faster than doing a KD tree rebuild. Be much faster.
So, do you have any libraries for this that you would recommend?
I would start with the dict, but you could do an LSH library or something.
yeah, like I said, is the other way to scale, like if you want to get to massive objects, massive points, right? So it's locality sensitive hashing, right? So basically, there's again a lossy technique where basically a lot of people use it in transformers now as well. So basically, rather than the hash avoiding collisions, you're hashing to points in space that are similar.
a lecture on that.
That was Anshuman. Yeah, Anshuman's big thing was LHS. LHS is also the solution to many problems. There are actually a bunch of open source implementations of that now, right?
Yeah, I was just
But
looking up, I just did fast LSH hash and Python, there's bunch
bunch of them, yeah.
Okay.
Yeah,
Right,
I
cool,
think
yeah, then I'll
that
do.
would be better than, just a crude partitioning of the space, because you're trying to encapsulate a surface but you're paying the penalty of a volume, whereas with LSH, you could, basically winnow that down to only storing the locations that make sense, as opposed to all the empty space.
Well, you wouldn't
Yeah.
store the empty space. With a dict, you wouldn't store the empty space. You just have only where the points are.
What is it?
Just a
Lookup table.
Look up there.
hash table.
Yeah, when you first said lookup table, I was assuming you were actually carving up space into volumes, and every one of those would have to be represented in memory.
No, you don't want to do that. Yeah.
That's what I
Yeah,
understood as well.
more like a hash table.
Yeah.
Okay.
Yeah, so
All right.
I understood the same thing as Kevin, so that's why I was confused.
Oh, sorry.
Yeah, no.
So you take the location, you hash that so that.
You get to some
Some
array
point,
point, and
yeah.
then there's the 5 points are right there.
Yeah.
Vivian,
Clever.
quick question. The inputs to the KDTreeSearch, are those like global XYZ coordinates, or are they like object specific coordinates?
Object specific.
All right, so you have a point on an object, and then you're querying for nearby points based on distance from the initial search point,
Yeah.
distance and direction. All right, okay. Okay.
Yeah, thanks a lot. Should I move on
Mhm.
to,
That's-
so,
it seems
yeah,
like it's a
actually, the
wall,
next
let's not go
slide is-
downhill from here.
Lawrence and I have an 11 amp.
Okay.
yeah. So, yeah, this is actually still related to the KDTreeSearch, but just to check in if this would change anything with what you're recommending. So when we're voting, we have a very similar problem, but the main difference is that we have to build the location tree at every step from the incoming votes. So basically, we have a bunch of incoming votes, and we want to query in that space of the votes, basically. So would it still be fast to like build up this discretized voxel space at every step, or is that, would you say something else would be better in that case?
What do you have to
What,
build
what
up
tree is
again?
being created?
Yeah,
So we basically get votes of shape v times 3. So votes are, if we threshold them, yeah, around 20 to 200, and then in that space we query these locations from the hypotheses.
but this is the part of the loop that was much faster already, right? This is a different, is it, it's using a completely different KD tree here, or is it the same KD tree you had in the previous slide?
It's a different KD tree. So
Okay,
in the previous slide, we could
Yeah.
build the tree once at the start of an experiment from the
Yeah.
model of the object. But now both the hypothesis locations that we used to query and the tree that we need to query in changes at every step. So here we would have
Right.
to build the
Have
tree
to-
or the voxel space or the lookup table at every step, basically.
So the first one was the evidence update from the sensory data, and this one is the evidence update from the module voting.
Yeah, exactly.
Okay, right.
but didn't you say that loop was already pretty fast?
Faster, but not as fast.
Yeah, so that one was, yeah. So if we threshold the votes, it's pretty fast because V is only up to 200 elements, so it's fast to build the tree anyways. But if we do use all the votes, which can be up to 200,000, then it's slower.
Is there an advantage to using 200,000? Would you like to use more than 200, or does it rapidly fall off? I guess, you know, is it, you know?
It's a minimal advantage, but not enough to justify the time cost.
I mean, neurons couldn't do that, right? They couldn't,
Yeah.
Well, I mean,
they couldn't process 200,000 votes.
Yeah,
So-
is the thresholding based on like an evidence measure or a confidence measure or anything like that?
Yeah, so basically only the most confident hypotheses get communicated to other learning modules.
And on average, how many votes is that per module that they're confident about?
It's between 1 and 200 usually.
Okay, all right, so you actually do have a lot. Okay, depending on
If
how, I guess how
this was-
symmetrical.
If this
Okay.
is being done by unions and an SDR, you can't get that high a number. You can't form a union of 200 hypotheses. You might be able to form a union of 50.
yeah,
I'm just saying it doesn't mean you couldn't do better than the neurons, but I'm saying the neurons are not, they're going to plateau at some lower number.
yeah. it seems
Yeah,
like-
yeah. The main problem is like if, like Eric says, if we have a very symmetric object, then all of the poses are about equally likely. So if we then threshold the evidence, they will all be kind of communicated or not.
Would there be a way of
That's just
compressing
here, for
those?
example.
Yeah, would there be a way of sort of consolidating those for which the evidence is all the same for a set of votes, like having like a list of like for the given evidence, you know, all of these possibilities are there. That way you don't have to no, never mind, I guess you have to expand it out anyway when you do the voting with other modules, so. I was just saying
Yes,
that if
so we
there's no
have
way
a
to distinguish two
mechanism.
votes from two hypotheses from each other based on the evidence, then they're functionally equivalent. There should be a way of compressing that down somehow.
Yeah, so we do have a mechanism to detect symmetry if two poses have consistently the same predictions, they're classified as symmetric after a certain number of steps, but still until they took this number of steps, it will still communicate a lot of votes.
Okay.
I'm almost tempted to say the right solution here is to not have so many hypotheses. It's like more an
Okay,
algorithmic.
Yeah, no,
Yeah.
so right now with the thresholding, it's actually pretty fast, so it might not be the highest
Right,
priority to
I mean,
optimize this one.
Yeah. Yeah, I agree.
Okay, then I'll move on. I guess just one last note on the KDTreeSearch radius is we only want points in a given radius, so specified by the maximum match distance. But we also want to get a matrix. And if we just query the radius, we get like a ragged list, since each point's radius contains a variable amount of neighbors. So what we do right now is to query for k nearest neighbors to get an array of shape h times k. And then we mask all the entries that are too far away. I guess there's really a better solution, but yeah.
Is this still relevant if we did the lookup table?
Yeah, I mean, in the lookup table, it can also happen that there, I mean, it will always be that within a given radius, there can be a variable amount of neighbors.
Is that a problem? Why is that a problem? No, it's not obvious.
Because then you can't use the matrix operations directly because they expect a fixed number of entries. You can't just put zeros there or something like that, or
yeah, but well, yeah. So yeah, I guess the two options would be either to fill up with zeros, but then if only one point has like 100 neighbors, then the matrix gets huge for all the ones that just have like 2 neighbors. And then I guess we do kind of the opposite and cut it off at a certain number of neighbors and then mask the ones that are too far away.
Isn't that what we were said to do earlier when we were talking about the lookup table?
Yeah.
Pick some number of points.
Yeah.
So,
Yeah, so that problem applies to the lookup table as well. It's yeah, I guess just a universal thing.
but you're saying if we did the query radius in principle, we'd have much fewer points.
In some cases, I mean, I actually didn't look at it in how many cases there are more points than k in the radius. It depends on how dense our models are.
Okay.
But yeah, maybe I'll move on. This one is not that much for speed. So now
Just a quick question. So right now you're assuming that you can't assign any importance to the points. They're all equal in your eyes as contributing evidence, right?
yeah.
What if you relax that assumption?
How
Well,
would you
the points get
distinguish them?
eliminated based on the evidence not fitting the hypothesis, right?
Well, I guess they contribute to addition of hypothesis, but I'm just thinking that in large flat areas, some of those points, it's like if you eliminate them, then you have gaps in your model. But if you had something that was higher order than just a point, then you could allow for something to substitute for a large flat area as opposed to a myriad of small points.
Right. This is the
Yeah, so
isolation problem I was talking about earlier.
Yeah, so I guess that's something that will come in more when we add hierarchy. That points, yeah. And then also when we build the models, we kind of take into account how fast features change in an area. So if we're just on a flat surface, we store less points in the model than if we are in like a part of the object where it curves a lot and features change a lot.
Yeah, I wouldn't necessarily postpone it to where you think of hierarchy, because then you're getting into assemblies of parts and stuff like that. What I would say is that if your fundamental primitive is starting to become burdensome because it's just too low information content and you need a lot of them before you get something out of it, it would almost like I would say that you would need to replace it with something that has more structure to it, so you don't need so many representations of it to yield a hypothesis. So I mean, something that's not a point, but just for argument's sake, a rectangle, that basically, as long as it's flat enough, it's the rectangle, and then the descriptor for the rectangle could basically subst for a myriad of points if things are flat enough. But because if you're going to go down to pixel points, the problem is you're going to run into these combinatorics. So unless you do some kind of abstraction, which I don't think is the same thing as hierarchy, it's going to kind of basically be a problem until you can efficiently represent a area of a portion of a surface by a few parameters as opposed to hundreds of points.
That's exactly what I was talking about in my research meeting last week, was how do you discretize a space using as few points as possible. You can use fewer points, the more high order information you're given, like say, in addition to giving the point, you're also given the gradient or the curvature. You can then extrapolate away from that point and represent a very large area near there if those features remain constant. But if the features start to change, like if the curvature changes or the gradient changes, then you might need to drop in another point there to capture that change. And then basically you could interpolate between those 2 points to get a smooth transition from one to the other.
Yeah, maybe that's a good topic for another research meeting to get into more. Yeah, because we only have about 10 minutes left, so I just want to get to the second topic real quick and see if there are any other thoughts on that, if that's okay.
Good.
So yeah, now the matrix operations. So the one that takes the longest is the einsum operation, which we use to get angles between the hypotheses and the observation. So basically, since we use unit vectors to calculate the angle, we basically just need to take the dot product between two vectors and then apply our cos to it. And we want to do this for all hypotheses, poses, and then nearest neighbors in one step. That means we need to apply the dot product between the hypothesis nearest neighbors, which is shape h times k times 3, and the transformed observations point normal. So 3 are the xyz coordinates of the point normal, which is a unit vector. And then, yeah, as an output, we want to have a matrix of size h times k. And einsum is basically just an efficient version of running a for loop over all hypotheses and then applying the dot product between the hypothesis point normal and the transformed observation point normal. Then we also apply normal dot products, for example, to rotate displacements by the hypothesized poses. So in that case, we have the possible rotations, which are 3x3 rotation matrices, and we have as many of them as we have hypotheses. And then we apply the dot product between that and the sense displacement, which is again a unit vector in xyz coordinates. No, it's not a unit vector in this case. It's just a displacement. And we get a matrix of size h times 3. We also apply matrix multiplications, for example, to get the rotation matrices from our pose hypotheses. So in this case, we have the poses stored in all the nodes. So that's number of nodes in the graph times 3 times 3. And then we have the sensed pose, which are also 3 unit vectors. They are orthonormal. And yeah, we apply a matrix multiplication between them to get n 3x3 rotation matrices. Then we have like the standard operations like addition, subtraction, arc, cos, sin, multiply to do a range of different things. Here the dimensions always stay the same. And then we have some reduce operations like applying the maximum to get the highest evidence in the nearest neighbor radius. So if we boil this down to just the size of the matrices, 2 things that I think could be places where we can maybe optimize something. So one thing is we don't need to test all hypotheses at every time step. So right now, since it's just matrix multiplications, we update the evidence for every hypothesis at every step. But in theory, we could mask a lot of the rows in the first axis, so h. And then the second one is some entries in K are also masked. Like I mentioned, if less than K neighbors are in the radius, then we mask these entries. So yeah, I don't know if you have any thoughts on that.
What are you using to do the matrix math?
NumPy.
NumPy, all right.
So with the first one, are you saying, like, how many rows are you trying to ignore on average? Like what percent? Because that seems like it's just brute force doing a lot of stuff that it doesn't need to do.
Yeah, so theoretically we could ignore a lot of these. So for example, we could only look at the n highest evidence hypotheses. So that could be 10, it could be 100, could be 1,000 highest hypothesis, whatever, but it would definitely be still lower than H, which is usually between like 1,000 and 40,000. Especially towards later steps in the episode, this would probably just be like 5 or so high evidence hypotheses.
So you really just want to, you only care about a very, very, very sparse subset of the rows.
Yeah.
So I don't know if there's a efficient way to do that.
I mean, the advantage of updating all of them at every time step is that you can easily recover a hypothesis, even if you get several inconsistent observations. But yeah, I'm not sure how relevant that actually is and if it's worth the computation.
I'd have to kind of take a look at the math to see if there's anything that pops to mind. It's hard telling from just a description.
Yeah.
Yeah, I would try to minimize the number of times you're calling arc, cos, and sine and so forth, because those are inherently a bit slower than sort of the built-in addition, multiply sort of things.
Oh, okay.
It's just because of the way they're implemented. They're usually lookup tables or something like that, because they're not something that you can just implement in transistors directly, like addition and subtraction and multiplication and so forth.
Yeah, there are a variety of things. I mean, when they're really computing the arc cos and you got floating point numbers, they start with the lookup and then there's probably a polynomial iteration on it. So they're expensive operations.
Like a small little Newton iteration. Yeah.
Right.
But
so
it
there's
is
a variety
more expensive. It's not a single op or anything like that.
There's a variety of optimizations that people go to try to compute that. The other thing is, if you take, I mean, the easiest thing is you take the dot product, which you say is normalized, and then just go to a lookup table to get you in the ballpark.
Yeah. The other thing is, if you're comparing distances, like if you're computing two distances and you're trying to compare which one's smaller, don't compare the distances like by, like when you have to like sum all the squared components and you take the square root, just compare the distances squared. That way you don't, that square root is also an expensive operation, and you can compare directly the distances squared. The one's gonna be bigger than the other, obviously. So that's another way you can save yourself some computations. If you don't actually need the distance, if you're just comparing two distances, you can get by with that.
Yeah, that's a good point. Yeah, because
that will tend to have a coordinate bias though to it.
How so?
When if you're just taking the distance, okay, I'm sorry. Never mind. I understand. I thought you were talking about the square of the components. Never mind. You're right. Yeah, compare the distances squared is easy enough.
So from the profiler, actually, the slowest operations are, or like multiplied by how often they are being performed in the algorithm, is the einsum, and actually I was surprised also the maximum operation.